Good. All right, so our final major topic on related rates. Oh, before I do that, I forgot. Get out your assignment guide. Assignment guide. There's a back too. Okay. So this is kind of important because we're talking about your homework that you have to do for this whole unit. So we did 3.1, 3.2, 3.3, and 3.4. Those were regular assignments on curve sketching. Okay. All of the rest of the homework that's on here, okay, is not anything that we're going to go over in class. Okay? You can say it's optional. Okay? But it's going to be extra practice. Here's the reason. You know, I've made these packets. We just did the one on rectilinear motion, and then we got a whole thing packet on related rates. That's what I'm considering as the homework that you have to do. Okay? The rest of everything else on here is just extra practice, that if you're like, yeah, I didn't quite get that, or I want to become a master, then this is where you would do the extra practice. I found bits and pieces of these questions throughout the book. Unfortunately, the textbook doesn't put them all into one place, so that's why it's not easy for me to just give these assignments.
What are we doing for chapter summaries?
For the chapter summary, you have to do, so circle these. This is what you have to do for the chapter summary. So 3.1 through 3.4, you have to do all four of those. 3.1, 3.2, 3.3, and 3.4. Then turn it over, and then you have to do 2.6. Related rates, that's what we're going to do today. You do not have to do a 3.6. Nope, that's just a summary. There's nothing new in that one.
Differentials and so on, so I can cover it next semester.
Yeah, I'm going to end up, I'll probably get a chance to talk about it when we get back, but it's a very small thing. Okay? So that's what's required of you, and that'll be due the day of the exam. Okay? If I were you, I'd probably jot down some of these other things in there, but they're not required. You know, because then it's all in one place. Applications of the derivative includes all of these things. Okay? All right, so that's the deal. So there's going to be no homework days where we go over homework. But if you do the homework and then you have questions, you can see me after school, and we'll go through them. Okay? All right, that's to give you the extra practice. Okay, now we're ready to go. So related rates is the next topic. And as you can see, we're going to cover rates that are related. What does that mean? Okay, so I'm going to demo this with a video. Okay, something that everybody has seen this, but you haven't seen it in slow-mo, I doubt. Okay, ready? Okay, we'll watch it again. This is what we're going to do for the rest of the hour.
Edit back. shows water droplets bouncing off the top of the water.
This one?
Yeah. Maybe turn the volume up. I'm not sure if they swear or not.
Hello, the internet. We are here with, alright Dan, little droplets of water that half goes on the surface.
Okay. There we go. Right.
How's it? There you go. Nailed it.
That's so cool.
What?
Harry. What are they doing?
It's just the way water works.
That is awesome. That's so cool. Did it again.
Water droplets do it again.
You just
No
keep on
way.
one.
You see it bounce?
There's more.
Yeah, watch that. Really looks cool. Oh. Oh, amazing. That is cool. And there's a little bubble that bounces off the big one and goes straight into it again. That is really cool. I didn't know that happened at all.
Yeah, it kind of it lets like half the water in, then it detaches and bounces, and then happens again until
that's
there's
amazing.
bugger all left of it.
Yeah.
Is it all gone now?
No, it's just a really small one now. Oh. That is so cool. I never knew that
You
happened.
didn't know they did that?
No. The mirror effect's really cool as well. It looks like someone's throwing a little ball that gets littler every time.
Yeah.
It's like, oh, I have a smaller one.
I'm going to give it to a kid, and by the time you finish it, it's not there anymore.
Bloody.
Okay.
I told you. No. There you go. Proof. Bet you feel like a right mug.
Okay.
That was going to make a
There's
mug
another-
joke, but that is in fact not a mug.
There's like a tab.
I was thinking the same thing.
How come it's going?
There's a tab at the top.
Yeah, you're right.
Fire top. There you go. Yeah.
That's
Oh, 10 top. What?
All right, I've got another. I got kind of carried away. I was looking at videos.
That's really
Please tell me you're watching the whole thing.
So
That can look around corners, beyond line of sight,
So this guy's talking about
body
sending
without
basically a photon
what we mean by a camera.
out of a light. Okay, now watch this.
And turn it on and off in 1/1,000,000th of a second, which is several femtoseconds. I'll create a packet of photons barely a millimeter wide.
That's a strip of.
And
That's a
that
trillionth
packet
of a
photons,
second.
that bullet, will travel at a speed of light, and again 1,000,000 times faster than an ordinary bullet. Now,
He's gonna shoot it
that
into this.
bullet and take
into
this
this
packet of
bottle.
photons and fire into this bottle. How will those photons shatter into this bottle? How does light look in slow motion?
So he's firing it here from the left. Just that little blip of light. And this is what it looks like. Watch it.
Now the whole event
Just sending, it's a trillionth of a second of light.
Now remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion. But Coca-Cola did not sponsor this research. Now there's a lot going on in
He's
this
gonna do
movie,
it
so let
again.
me break this down and show you what's going on. So the pulse enters the bottle, our bullet, with a packet of photons. They start traveling through and they start scattering inside. Some of the light leaks, goes on the table, and you start seeing these ripples of waves. many of the photons eventually reach the cap and then they explode in various directions. As you can see, there's a bubble of air and it's bouncing around inside. Meanwhile, the ripples are traveling on the table. And because of the reflections at the top, you'll see at the back of the bottle, after several frames, reflections are focused. Now, if you take an odd...
So it's 11 minutes long if you want to look at it. But that really doesn't have that much to do with what we're doing, but I just thought it was cool. All right. So what I want to do today is I want to kind of explain what kinds of problems these related rates are. And then we're going to do a little math with it. So let's first consider the dropping of the water droplet into the basin of water. So if we have a circle, okay, if we drop the water into the circle, into the water, okay, the droplet of water into the basin of water, it starts to form the circles, right? Now, what's really going on here is there's multiple things going on, okay? So this is what we're going to focus on, rates that are related, okay? So the first thing I want to identify is the fact that if you could identify the middle of the circle, there is a radius for the circle. But does it make sense that as the circle expands, that the radius is traveling at a certain rate? Okay, it goes from what would have been a smaller one here to, a bigger one here, so on. So what's happening here is that the radius is changing. Okay, so radius is changing. If something is changing, then we can measure it. We can tell how fast it's going. Okay? So if we put a little speedometer on the radius, we could measure how fast it's changing over time. And when we do that, we can label it then. So what I'm going to say is the radius is r, therefore dr dt is the rate that the radius is changing with respect to time. Write that one down there. Dr dt means the rate that the radius is changing with respect to time. Now we can measure that feet per second, inches per second, whatever, miles per hour if we wanted to. We can put a measurement on it and it's a rate. Okay? And the rate is always per some unit of time. That's what the T is all about. Okay, now that's only one thing. Does everybody agree that there is a circle for every radius? And every circle, we can calculate its area. So wouldn't you say if this is time equals 0 when this thing is dropped into the middle, that at time equals 1 there's a radius, and so that means there's a circle. And then at time equals 1.5 or time equals 2, there's different circles at different times. In fact, it's constantly changing. And then we can calculate the area of the circle at any given one of those times. So what we can say is that the area is changing. The area of the circle is also changing. Okay? So the area of the circle is changing, and we use A for area. So we're going to say dA dt is how we're going to name the fact that the area is changing with respect to time. Because time is key here. This is time equals 0, and then as time goes on, we have different areas for each of the different circles. And it's continuous. It's instantly changing. Okay, besides area, we have circumference. So you can fill in the blanks here. Circumference is changing. And of course, circumference uses c. And so how do you suppose we name that? dc dt. So anytime you see something like this, dr dt or dA dt or dc dt, what it means is that's a measurement of how fast the r, the a, or the c are changing as time goes on. Now here's the question that was asked by the guys up there. I know that the circle is changing, the area is changing, the circumference and the radius are changing. I wonder if they're related in any way. Seems like they would be. Okay? So the question is, how on earth are they related? Well, here's what they came up with. It's pretty cool. Let's consider area. Okay. The area of a circle is A equals pi r squared. Well, this tells you that the area and the radius are related. If you know one, then you can compute the other, right? And it doesn't matter which one that you know, you can always go backwards and figure out the other one. But that's just the exact area and the exact radius at any single precise moment. If you stop time, we calculate this. And that's all pre-calculus stuff. Pre-calculus just says, tell me what the area is. Calculus is, how fast is the area changing compared to the radius at any given moment, and how fast the radius is changing. So I'm going to show you how to take a derivative with respect to time. Okay? So this is a completely new kind of derivative. Well, not completely new. It's a new derivative where we're going to use t as our main variable that we're taking the derivative with respect to. So watch this. We're going to do lots of them, so this is just the first one. We're going to take the derivative of both of these sides with respect to t. Okay, so watch this. We're going to pretend that a is a function of t, so we can say the derivative of this is dA dt. So the derivative of the left side is dA dt. We're saying that, let's pretend that a is a function of time, which it is. The area at any given time is based upon the time that it is. Okay? Now, this is the part that's kind of tricky. The derivative of pi r squared with respect to time, you actually have to go back to the chain rule and falling apart there. And think of the fact that the radius is also a function of time, because how far the radius is out is also dependent upon what time it is. So this is how we do it. We do the derivative of this with the thought that r is also a function of t. So the derivative is 2 pi times r to the first this is where the chain rule part comes in. Now we multiply by the derivative of r with respect to t. So it's dr times dr dt. And this is how the rates are related. What do I mean by that? Well, remember how we said that the area changes as time goes on? Well, to find the exact rate that the area is changing by, you take 2 times pi times whatever the radius is at whatever moment that you want to pick, and then you multiply it by the rate that the radius is changing by. You multiply those 4 things together, and that tells you how fast the radius, that the area is changing by. Okay. We're going to go through some examples. This is just the intro one. Okay. All right, I'm going to do another example. I'm going to do this one on the back board. So, follow me. So, the next example is a triangle. Okay? We're going to make it a right triangle. And so I'm going to label these 3 sides of the triangle as x, y, and z. Now, x, y, and z, since they're the 3 sides of a right triangle, are related. How are they all related? Pythagorean theorem. So the lengths themselves are related by x squared plus y squared equals z squared. Okay? That's how the sides are all related. But now, I want you to imagine that I did this like on a smartboard, and each of the endpoints I can grab and I can drag them. Okay? So I can pick this point up right here and I can move it over here. You know what I'm saying? If I take this and I move it, then I'm going to create a new triangle. And the new triangle is going to go out to here, and it's going to go here. You see it? Now, if I just move it and I hold it there, I've created a new triangle, and they're still related this way, x, y, and z. Just that y got longer. Okay? Now I want you to imagine this. I want you to imagine that as I move it, as I move the dot from here to here, we can measure how fast I'm moving it. So as I'm moving it, aren't I making lots of different triangles? You know, it's like the slow motion thing. As I'm going here, I'm making all these different triangles. And it's continuous because I'm just moving, and there's always a triangle there. So if I move this at a constant rate, I wonder how the area of the triangle is changing with respect to how fast I'm moving y. That is, at any given moment, there's an area, and the way that it looks, the area is always bigger than the area before it. But I wonder how fast the area is changing. Okay? And how it is related to this y. Well, here's how we can label these, and this is just so kind of cool. X and y and z, if y is changing, okay, if y is changing, then the name that we give it, the name we give to the rate is dy dt. It's how fast it's changing. It's a rate. It's the rate that the y is changing. Now, if I have the original triangle and I make y longer, then dy dt is a positive number because y is getting bigger. But if I go in reverse and y is smaller, then dy dt is a negative number because it's becoming less and less. It's bigger. It went from a longer value to a smaller value. It shrunk. So dy dt, the rate, is negative. But now imagine this. This is kind of funky. What if I started making, well, when I move y, doesn't that automatically make z change? Yeah. So if I change y, then z changes. That means that z has a rate, and its rate is dz dt. Now, if I really want to mess with you, what I'll do is I'll grab this point, and I'll grab this point, and I'll move them both at the same time. Maybe make one longer, the other one shorter, and I'll do it at exactly the same time. And I'll maybe make this one go out really fast, and I'll make this one go down slow. And so what I have is that x, y, and z are changing, and we can label them as rates as dx dt. This one is dx dt. So we agreed that at all moments we can calculate an area, and the area is changing, and the area is dA dt. The rate that the area is changing is dA dt. So I wonder how they're all connected. Well, what's cool is we can take this equation right here, and if we find the derivative with respect to t of both sides of the equation, we can find out how the rates are related. That is, how fast each one of them are moving. So we're going to do that right now. What is the derivative of x squared plus y squared equals z squared if we take the derivative of both sides with respect to t? So that means x is a function of t, y is a function of t, and z is a function of t, meaning that time influences how long each one of them are. Here's the derivative. 2 times x to the first. That's our normal rule. Then we're going to apply chain rule because a t is buried inside of each one of these. 2x dx dt plus 2y dy dt is equal to 2z dz dt. Right. Area formula, in this case, we can do it as 1/2 times x times y. This one we'll do tomorrow because we're going to run out of time. This one requires us to do the product rule to find the area of that triangle and how it's changing at any given moment. Okay, that packet, we're going to work on that packet tomorrow.